start the recording. All right, so we are in section 2.3 now, linear equations. We talked last time about how to solve differential equations that are separable. And that's a wonderful thing, that approach, because a lot of very common, important differential equations are separable. But nevertheless, we do need to have other approaches to solve linear differential equations. And if you have linear differential equations of the first order that are not separable, section 2.3 gives an approach on how to solve those kind of differential equations. We're going to go over an example, and we will discuss it. So let me give you a moment to copy that down, this example. And like I said, there was a question from Michael in the chat window. We'll discuss the particulars of your first exam, which is going to be ready to go Thursday after class. But we'll talk about that towards the end of class, okay? All right, and then there'll be a little time to answer some questions too. Okay, great. Let me give you a moment to copy this down. Yeah, this Thursday, Michael. This Thursday after class. That's right. That it'll be ready. Sorry, I meant to say this Thursday after class. Yes. That's when your exam will be ready for you to take. All right, no problem. Okay, so and incidentally, your exam will cover chapter 1 and chapter 2 up to and including this section 2.3. But let's look at this. So we have this differential equation. It's a first order differential equation. And if we were to rearrange the terms, we would see that it is a linear differential equation as well. It meets the conditions for a linear differential equation that we learned about in chapter 1. But is this differential equation separable? Is this a separable differential equation that you see here? Is it possible to separate the variables? Yeah, I agree with Antonio and a few others, and Michael. Yeah, I mean, let me just see here, one moment. Yeah, I do not see a way to separate the variables on this differential equation. So that means we're going to need another approach to solve this differential equation. Let me show you how we're going to solve this differential equation. All right, I'll go to the next page. Very good. Thank you, Matthew. So again, note, although this differential equation is a linear first order differential equation, it's not separable. And so we're going to use an approach called an integrating factor approach to solve the differential equation. And there are 4 steps towards this integrating factor approach. So let me let you get, caught up here a little bit in your note taking, and then we'll continue on with the problem. Okay, so there are 4 steps towards the integrating factor approach. And the reason this approach works, it's going to be, I think the example is going to motivate why this approach will work. But first thing we have to do is we have to take the differential equation and write it in this standard form. Okay, this is the standard form that we need to write our differential equation in. And you can see that right now our differential equation is not in that standard form. So what do we have to do to get the differential equation in standard form? What is necessary to do? That's right, Matthew and Wajija. We have to divide x so that the derivative is by itself. And so that's what we do. We're going to divide through the differential equation on this step here by x. But immediately I'm going to note that since we are dividing by x, the largest interval over which a solution would be defined would be 0 to infinity. Now, another option I will mention, you could also say, and it really is depend on the initial condition, but you could also have, what's another possible largest interval that you could have?
Negative infinity to 0.
Good, Justin. Negative infinity to 0. So which interval you would choose would depend, like if you were given an initial condition in addition to the differential equation, that would tell you which is the right interval to choose. But in WebAssign, what they traditionally do is if you're not given any initial condition, then, which do you choose? 0 to infinity or negative infinity to 0? You'll choose 0 to infinity. Okay, just to, let you know that. Again, I think WebAssign should really allow for 2 answers, one or the other, but they only allows for one. Choose the 0 to infinity in this case, since you don't have an initial condition. Okay, then we will, well, now we have our function of x, p of x term, okay, which is -4 over x. That's right, Zachary. 0 to infinity is by default. That's what I meant to say. Yes. Thank you. So now the differential equation's in the standard form. Okay, one moment. All right, it's in a standard form. And now I have to go to the next page. In other words, step one is done. Step one is done. Step two is we have to find what's called the integrating factor. I mean, are there any questions so far? Very good. Are we ready to move to the next page? All right. Well, then let's go ahead and move to the next page. Very good. Okay. So the integrating factor is denoted by this symbol mu of x. Mu of x. So mu is a function of x, and it's defined as e to the power, and the power is this integral of the p function. That's your power. That's how the integrating factor is defined. And so we know what p is. Our p function is -4 over x. Let me see. Matthew says that's correct. Hold on. If we go back, I'll come back here. If we go back, the p function is the coefficient function in front of the y. And, you know, if you had, like, say, a 1 in front of the y, or say you had a 5 in front of the y, then 5 would be your p of x. Okay, it's whatever function comes in front of y, the coefficient of y. And so -4 over x is our function, our p of x function. And, okay, so I'm going to then integrate. I'm going to integrate. So, of course, I'll factor out the constant, the -4. And 1 over x becomes the log, the antiderivative is technically the log of the absolute value of x. But remember, we're assuming x here is positive. And I guess actually, I think I'm going to qualify something I had said here. Maybe going back. Let me go back here. Remember how I said we could have 0 to infinity or 0 to negative infinity? Well, I agree with Zachary, based on what I've seen in the web assigned homework, that 0 to infinity, in this case, is the default answer. But there's also another reason it should be that. It's because the antiderivative, well, no. I want to be a little bit careful on that. Well, the antiderivative is the log of x, and that we don't need to have the antiderivative of 1 over x is normally the log of the absolute value of x, okay, plus a constant. But since we're assuming that x is greater than 0, okay, then we don't need to carry the absolute values. So that's another reason, you know. Traditionally, like when you do the integrating factor approach, you don't use the log of the absolute value of x. You just have, like, the integral of 1 over x is just the log of x. But then, of course, that restricts your interval definition. But also, you do not need to worry about the constancy of integration for the integrating factor approach. It turns out that essentially it is irrelevant it's not, well, I'll say irrelevant for the procedure. You could let c equal 0, for instance. Okay, so okay, so we're here now. We're here. And I have to rewrite this. I don't want to use e to the -4 times the log of x, because I can simplify that. Okay, so the power is -4, or the coefficient of the log of x is -4. So by the log rules, this equals e to the log of x to the -4th. But then the exponential and log function simplify out, leaving you with x to the -4th. Okay, and that's your integrating factor. Let me know if you have any questions.
Yes, Professor, if you can go through the integral that you did. Let me see. So we're taking the integral of the coefficient of y. Am I right?
That is correct. That is correct. That's absolutely right. So the coefficient of y, okay, forgive me for that noise. The coefficient of y was -4/x, right?
Yeah.
So we're doing the integral of that rational function. And that's going to equal -4 times the log of x. So are you good up to here, Thomas?
Yeah, but is that e to the integral of -4 over x?
Now the integral of 1/x is the log of the absolute value of x. But we only have the log of x because we don't need the absolute value. I think I'm getting some blowback on your side, Thomas. I don't know if you don't have your radio on or anything, do you? Yeah. The integral of 1/x is the antiderivative is of 1/x is log of x, because it's normally the log of the absolute value of x, but we're letting x be greater than 0. So I just get an this is just the antiderivative of 1/x is the log of x. So you understand the e stays. You notice the e stays where it is, and then the antiderivative is the power here. Is that okay? Is that all right?
Yes. Yes. So the answer is x to the -4.
That's right. That is your integrating factor. And now, why did we get that? Because what we're going to do in steps 3 and 4, we'll do them together. We're going to multiply both sides of the standard form equation. And what I mean is that's the standard form of the differential equation by that integrating factor. Okay? And then we'll integrate to solve for y. This is really a fascinating, what you're going to see here. This is really, truly fascinating. Remember this was the standard form of the differential equation, right? That was the standard form. So the standard form is always dy dx plus p of x times y equals f of x. That's the standard form for section that you have to that for section 2.3 of the differential equation, and this is what the standard form was. Now what we're going to do is notice what we're doing. We're going to well, that's right, Michael. Very good. That's absolutely right. Michael's talking about an expanded product rule. He's absolutely right. We're multiplying through by x to the -4th through the equation. Paige, question?
Yeah, sorry. You might have already said this, but I was having a little bit of trouble hearing you. Why are we raising it to the e power for the p of x at the top? Like, is it always going to be e to the p of x, or the integral of p of x dx?
It's always going to be the integral of e. It's always going to be this. Yes.
Okay, thank you.
Sure.
That's just
no
like an
problem.
elegant solution, right?
That's right. It turns out it works. It turns out this works. There are reasons, if you look at the proof in the book, there are reasons why it works. But I think by looking at this example, you'll see why that works. If you want to like see the proof, it's in the book. But for now, let's focus. But it is elegant. I agree.
Yeah, because it probably makes the fourth step super easy, right?
That's right, Matthew. That's right. Because look what happens here. We multiply through by x to the negative fourth. And incidentally, my volume, I know I guess I had it down a little bit at the start of the lecture, but were you able to hear me okay? I think I mean, overall, my voice was a little light, but was it, okay, all right, good. All right, so, yeah, I gotcha. Well, I keep my volume at normally 50%. Thank you, Christopher. So that, but then if you lower your volume, then that's fine. So look, this is what we got. This is what we have. Now, okay, the left side is very interesting. This left side of the differential equations, very interesting. Okay, and what I want to do, I want to go to the next page and show you why it's interesting, because you're going to see why. Let's see. Michael says, I think we want to convert a non-separable equation to one which is separable. A non-separable differential equation can't be made separable, at least not that I know of. Or if you did, it would be maybe a big mess. There was a problem in your homework where you had a problem where you had the answer involved the tangent function, the final answer, but you could make it separable and integrate. But this is not easily separable. Right. Well, Michael, let's go to the next page and see what happens here. All right. So here's what we had on the left. We had x to the negative fourth times dy dx plus negative 4 times x to the negative fifth y equals x times ex. Look at what the left side is. The left side is actually the derivative of x to the negative fourth times y. It's the derivative of this product. I mean, convince yourself of it. If you take the derivative of x to the negative fourth times y, okay, and you use the product rule on that, you're going to get, I mean, remember, the product rule, if you have the derivative of the product f times g, that's f prime times g plus f times g prime. So looking up here, this is this here is f prime. This here is g. This here is F. And this here is G prime. Because x to the negative fourth is F. And Y is G. All right, are there any questions on that? Are there any questions on that? Who's feeling comfortable with this step here? Let's see, Zachary says, why is the last step not just to multiply by x to the fourth? Well, the integrating factor, Zachary, was x to the negative fourth. So that on the previous page, we multiplied through the standard form of the differential equation by x to the negative fourth. But the beauty is the left-hand side is really, the left-hand side of the differential equation is the derivative of a product. Okay, it's the derivative of a product. I mean, I want to maybe give me a few thumbs up if you're comfortable with this step here. They're all going to work like this. They're all going to blossom out like this. But I want to make sure you're comfortable before I move on. Okay, Wajija's comfortable. Matthew's comfortable. Antonio. Okay, it is Christopher. All right. Well, then let's go on because we do have another page here. All right. Zachary, are you okay? Thank you, everybody. Zachary, you're good? Okay, wonderful, wonderful. Okay, so now on the left, now what I'm going to do is I'm going to integrate both sides. I'm going to integrate the left side and I'm going to integrate the right side of my equation. And on the left side here, okay, on the left side, so I'm integrating both sides of my equation. But on the left side, I have the integral of a derivative. Well, when you take the integral of a derivative, what do you get?
Just the function.
Just the function. That's right, Justin. And that's what we have right here. And so that's what comes out. And you see, now you'll be able to solve for y, because all you need to do after we integrate the right-hand side of this equation, all we need to do in the end is divide by x to the negative fourth. So on the right-hand side, how do we integrate x, the integral of x e to the x dx? Well, got to use integration by parts on that. So we let u equals x and dv equals e to the x dx. Then du equals dx and v equals e to the x. And so, as you know, the integral of u dv equals uv minus the integral of v du. Okay. To be honest, Matthew, I forget. But we'll just keep going forward here, and we'll see. So, all right. Now, here, you know the antiderivative of e to the x. That's e to the x. And so you get to right here. And now I divide that equation by x to the negative fourth. And now I see we do have another page. But let's make sure people are comfortable up to this step here. Are there any questions up to this step? Have we solved the differential equation? Have we solved it? Okay, Christopher, no problem. We have. Now we know the explicit solution. However, I think we should try to simplify the terms in this solution. That's right, Matthew, absolutely correct, because we have y equals, we have an explicit solution. And that's right, Zachary, we are going to simplify the terms. And that's where, on the next page, we'll simplify the terms. Because I'm with Zachary, I like positive exponents in my final solution. Notice I have a capital C here, okay. WebAssign, does it take, it likes capital C, right? Okay, I think WebAssign likes capital C. Does it take a lowercase c? Or does it like I think it likes the capital C's, right? Normally. Oh, it also will take lowercase, okay. All right, very good. All right, both equally fine. All right, no problem. Matthew uses the lowercase, that's fine. Now Zachary says sometimes it wants a capital. Well, yes, it might specify use a capital C. Technically, there's not a difference between a lowercase c and a capital C. They both stand for constants of integration. I tend to like to use the capital C. But remember, in WebAssign, you have to always look at those instructions. So like when you're, taking your exam and you have one attempt to get the answer right, make sure you look at the instructions before you submit an answer. That's just, but all right, well, let's proceed on. May we go to the next page? All right, let's go to the next page. Very good. So on the next page then, this here is the solution. And, x is greater than 0. So we have to add that. We can't, well, like if you were to type the answer in WebAssign, you would just type the answer. But in our minds, we know that there is a restriction on our solution, that x is greater than 0. But there are a few things that are asked then about these kind of solutions that are going to be asked in the WebAssign homework. We want to know if we have what are called transient terms. What's transient mean if something's transient?
It means that it diminishes as time goes on or as the values of x get larger.
That's absolutely right. That's absolutely right, Michael. A transient term would be a term that in the solution that disappears as x gets large. But all of the terms here, all of your terms these are not transient terms. Okay, they don't approach 0 as x gets large. Examples of transient terms would be like terms like c times e to the negative x and c over x to the 4th. So, and Michael made a good point in the chat window. So, you want to see if you're like, you want to know sometimes, well, a lot of times what your steady state solution is. So that you solve a differential equation, you get a solution, but what happens to the solution over as x gets large or as time gets large, say? That would be your steady state solution. And yeah, so are there any questions on this procedure? Okay, Christopher's good. Now, of course, we haven't done an initial value problem, but you know how to do an initial value problem. So
I do have a question, Professor.
yes, Tom. Yeah,
You said that it was a four-step process, right?
it is a four-step process. That's correct.
So what will be actually the fourth step? If we would put
Well, we combined steps 3 and 4 together. Tell you what. Let me get the ebook here. Hold on.
okay.
Your question's a good one. Let me bring up the ebook.
Step 3 was to multiply both sides of the standard form of equation by mu of x, and step 4 was to integrate so we can solve for y.
That's exactly right. Exactly right. Let me just one moment here. All right, so I'm going to go into the ebook if that's okay. All right, let me go in there. Hold on. Excellent. One moment. Let me find our section here. 2.3, linear equations. So they go through the method of solution. They go through the why this process works. You're welcome to look at that. I think by doing enough examples, you'll get a feel for this, for why, as well. Why you choose that integrating factor. But Thomas, here, do you see here the 4 steps written out here?
Okay, so integrate both sides of the last equation and solve for y.
That's
Okay.
correct. That's correct.
Got it. Thank you.
Sure, you're welcome. You're welcome. So we can, the book has a lot of nice examples. Let me just see here. One moment. We actually did the 3rd example from the book. I want to go and look at example 4 actually. So let me go in the book here to example 4. Okay, find the general solution for this differential equation. Okay, so the first thing you want to do, and you don't have to copy this example down. I mean, it's going to be in the recording. It's in your book. First thing you do is you get the equation in standard form. And now your p of x function is equal to x over x squared minus 9. Okay. Now, p is continuous on 3 intervals, but they're going to focus on solving the equation on the 1st and 3rd intervals. Okay. So here's the integrating factor step. All right. And let me ask you something here. I'm going to go to the whiteboard, and I'm going to look at that integral of x over x squared minus 9 dx. I'm going to go to the whiteboard. Because they just kind of put an answer there, and you know that I like to see work for the exam. I'm going to want to see work and steps. Remember, the textbooks always, well, a lot of times they leave out important details in the solution. And, I like to see the details. I like to see that you fully understand. So how would you do this integral here? What approach would you use? Would you use partial fractions? Would you use substitution? Would you use integration by parts? What makes sense here?
Use substitution.
Good, substitution. Let u equal x squared minus 9. So then du dx equals 2x, and hence good, Matthew, hence du is 2x dx, and so 1/2 du is x dx. So this is the work that the book solution leaves out, right? That I would want to see on your exam. So, okay, x dx is 1/2 du. So we have 1 over u times 1/2 du. Okay, so if we call our little integral, well, I mean, this is our integral, right? Then our integral is this. Factor out the 1/2. Now you have integral of 1 over u du. And I'm moving through this rather briskly because you should know this pretty well. So now you have 1/2 times the log of the absolute value of the absolute value of u. Hold on, I got to be careful here. And you don't need to worry about the constant of integration. And so you get 1/2 times the log of the absolute value of x squared minus 9. Okay, and if we assume that x is greater than 3 or x is less than -3, which is why in the solution they say this is example 4 in section 2.3. Before we had done example 3, that was our last example, but this is example 4. In example 4, they're saying we shall solve the equation on the first and third intervals. So that's these intervals. And they're doing that so you can drop the absolute value. Okay, so you do have to worry about the absolute value, and you'll need to worry about it in your work. And if you're dropping the absolute value, you have to justify why you're doing it, just like I did here and like I did on the last example. But are there any questions on this before we finish up the example?
Yes.
Michael? Yep.
To get rid of the ln, Professor.
Oh man, I'm sorry, I put the ln here. Good catch. Yep, thank you. The ln has to be there. Thank you, Thomas, for catching that. Yes, my mistake. The ln is there. Nope, did not disappear.
Okay, thank you.
Okay, all right. Okay, now Hubong's saying that it's not going to become a power. That's right, because this is going to. What would this equal? Well, I mean, I guess actually I can go down here, right? This would equal. I mean, there's no reason for students to get tripped up over these kind of problems. The 1/2 becomes, by the log rules, you know, the log rules, if you have the log of a to the bth power, that equals b times the log of a. Right? How many remember that rule from their pre-calculus days? I hope maybe I get one positive response on that. All right, thank you, Matthew. Thank you, Ann. All right, tiny bit. All right, Andrea. Now, look here. We can write this then as the log. We can write this as the log of the square root of x squared minus 9. Okay. And so your integrating factor was equal to then e times, hold on here. Yeah, the integrating factor is e times the e to the raised to the power log of square root of x squared minus 9. And then that just equals square root of x squared minus 9. Okay, are there any questions on that before I get back to the problem? Okay. All right. Well, then let's go ahead and get back to example 4 in the book. Then, if we're good with that. Right. All right. Let me see here. Let me go back to the book. Okay. So here then, you know, there's how, you know, square root of x squared minus 9, right? Hold on here. I mean, and you know, they left out work on how to get that, but you know, I want to see that work on the exam. Okay, but okay, now of course you multiply through you multiply through equation 8. Here I put it in pink by the square root of x squared minus 9, and that's going to then hold on here. Yeah, they're leaving out steps. They're leaving out steps. I'll go back to the whiteboard and put in the steps. Hold on. I'm actually very happy I'm doing this example. As the second one. Let me go. So what I want to do is I want to justify this step here. I want to justify that step there. So let me go back into the whiteboard here. And they multiply through square root of x squared, square root of x squared minus 9. That's your integrating factor. Okay, you're multiplying it through the standard form of your differential equation. See, advanced books, they always assume students, at your level, you can fill in the details. So that's common for examples, the solutions of examples in advanced books. That's common. They're trying to, save a little paper. There's that integrating factor. We multiplied it through. So this term here would, well, no, let me just write it here. Hold on. Okay, so we have the square root of x squared minus 9 dy dx. Okay. 0. Zachary, this is a 0 here on the right-hand side. In the parentheses, that's a 0. Okay. Then here we're going to have. Let me just see here. One moment. Let me write this a little bit differently. Hold on. I'm going to write this as x squared minus 9 to the half power plus, okay, and then this is going to be x squared. The second term will reduce to x squared minus 9 to what power? What would the power be? X squared minus 9 to the, so take square root of x squared minus 9 divided by x squared minus 9. What's the power going to be? Not a -1, but I appreciate all answers. -1/2. Good. Good. Okay. And so, let me know if you have any questions on that. On the left-hand side, now, this is the derivative of hold on here. This is the derivative of x squared minus 9 to the 1/2 power times y. If you use the product, so when you differentiate this product, you use the product rule, and the product rule is going to give you this here. Okay. And now you integrate both sides. You integrate both sides. Okay, so you're integrating on the left the derivative of the square root of x squared minus 9 times y with respect to x. And on the right side, you're integrating 0 with respect to x. Okay, let me know if you have any questions, please. So what you're left with is x squared, the square root of x squared minus 9y equals what? What's the integral of 0? What would that equal? Good. Good, Zachary, a constant. And so y is equal to the constant divided by the square root of x squared minus 9. And we're allowed to divide by that because we're assuming, well, we're not assuming x equals 3 or negative 3. And there's your solution. There it is. And I guess we can add the qualifier that either x is greater than 3 or x is less than negative 3. Okay? How many found that helpful, my working that out a little bit for you? Was that helpful, for example, 4? Thank you, Max. I appreciate that. Thank you, Christopher. Thank you, Thomas. Thank you, Antonio. Thank you, Andre. Okay, and Wajisha, that is correct. You always are going to have, after you multiply through by the integrating factor, the left-hand side of your equation will be the derivative of a product of two functions, one of which is y, the y variable. And that's the beauty, because then when you integrate both sides, which is of the equation, which is step 4, you get an expression on the left where you have the y there, and you can always then solve for y. It's really a beautiful approach. Okay, so then on that note, let me go back to the book. Okay, and hold on here. So now, final comment. Thus, on either the interval negative infinity to negative 3 or 3 to infinity, the general solution of the equation, of this differential equation, is y equals a constant over the square root of x squared minus 9. Okay, thank you, Christopher. Are there any questions? I mean, if not, I'll stop the recording.